So my name is Eric Carlson, and I work for the WSP Nuclear in Finland. I've been with WSP since 2023, and I work mainly in siting and permitting issues for SMR and large-scale nuclear.
Yeah, and my name is Jonas Wallman. I've been at WSP since 2016. I work as senior manager for the Energy and Nuclear Advisory Department in Sweden, and also represent the Nordic for WSP Global Nuclear Services. I'm an energy engineer, been working with nuclear projects locally and globally in new builds, safety upgrades on existing facilities, decommissioning, and waste management projects. I've been involved in different phases and matters. But let's go to the presentation and the agenda. So in this webinar, we will give you an insight into small modular reactors and how SMR has emerged as a possible solution to reduce global carbon dioxide emissions and reduce the environmental footprint. And WSP is involved in several SMR projects around the world, and we work actively to support industries and reactor developers, municipalities, and energy companies with a combined mix of local and global skills and experience. As the majority of our projects are confidential, we have today chosen an agenda where we start with a short introduction regarding the technology and the need for this technology to meet the global environmental goals, and how industries can use this technology as part of their journey to net zero. We have also put together a hypothetical question from a hypothetical industry client, where we generally go through an example of an approach for an industry to go from idea to reality. And we end up with some Q&As, as Anthony said. So briefly about WSP, we are a world-leading consulting company with 70,000 employees around the world, where our competence in environment, geology, technology, infrastructure, design, project management, advisory, etc., provide conditions to work with the entire nuclear life cycle. As shown in this picture, with some examples where we today contribute in different assignments with different clients regarding nuclear. And as I mentioned, we are a global company. So, and within nuclear, we have been involved in nuclear projects in a lot of different countries, and with some of those countries showed in this picture, and with what kind of subjects and experience. So before we get into small modular reactors, we would like to briefly mention that large-scale nuclear power has not played out its role. It will continue to play a very important role, and in many cases, the absolute best option. However, they are especially adapted for electricity production on a large scale and use the economy of scale to be profitable and a long-term investment. With large-scale nuclear power, it often comes with higher demands for adapted sites, infrastructure, and large investment. And that is parameters that can make the case unsuitable for an industry. And on this slide, the nuclear power makes a very small footprint on the environment and has several advantages for protecting biodiversity, which is illustrated in this picture. And in this case, there is a large-scale reactor in relation to solar and land-based wind with regard to land use. However, it should be mentioned that the case may vary depending on different technical solutions, but the difference in all cases will differ in magnitude. And this is important to mention due to the importance of biodiversity and land use. So what is a small modular reactor? Simplified, you can say that it is a reactor with a lower power output from 5 to 300 megawatts, and in some cases even more than that. The developing focus have been on modularization and standardization, Safety features has been increased in the advantage of a smaller core. Opportunities for greater flexibility has been created when it comes to siting, and simplified licensing and deployment has been made. And with this focus on the design of a SMR, a lower capital investment than for a large-scale reactor is reached. And it is these parameters and changes said in previous slide that are necessary in order to be able to depart from the otherwise profitable parameter of maximizing the power output from each built reactor, in the same way as we work to increase the power output from each wind turbine that is installed. And this is what we call the economy of scale. So small modular reactors has really shown its advantages in theory. And this is why we now see several developers and projects emerging around the world. And this picture gives an overview of which countries are developing their own reactors and countries that are not developing their own reactors, but has expressed an interest in SMR deployment. So the degree of maturity among the reactors is different, and so is the status of the projects. So globally, there is about 56 projects in early development, 20 in advanced development, 3 under construction, 2 test facilities in operation, and 3 reactors in operation. But this is changing very rapidly, and I'm sure that these numbers already have been changed, and those changes are in a positive direction for SMR deployment. As you can see from the picture, there are also different types of reactors with their different advantages. And here you see a list of number of water-cooled, gas-cooled, fast reactor, molten salt reactors, etc. under development. The circular diagram also shows the number of reactors within different power outputs to cover up different kind of needs and design opportunities. So the industry and power industry is a big part of the global CO2 emissions. Those are also sectors that has had difficulty to adjust to fossil-free, and partly due to its need of high quality energy, which is most often generated by burning fossil fuels. So the global industry accounts for roughly 24% of the global greenhouse gas emissions, and the industry must find solutions to reduce its energy needs, but also to switch the use of fossil-free energy. And it is clear that the industry knows about the situation and from there sets their own requirements and environmental goals. And some examples of industries that has really big energy demands is this iron and steel that requires smelters and huge amounts of energy, and extraction of oil and gas that has large steam requirements, as pulp and paper plants also has high requirements on steam and energy. Production of aluminium and copper, etc., require very large amount of electricity. Other industries include, for example, mining and data centers that has a lot of electricity as well. As earlier mentioned, countries as well as companies have made commitments to reduce their CO2 emissions, and staying below the 1.5 degrees target requires a 45% reduction by 2030 and a net zero by 2050. And moving to renewables and nuclear electricity production can get us part of the way there. And an increase of fossil-free energy production must be addressed. So what does the toolbox look like for nuclear power to be able to contribute in the same way as it contributes today, but also to be developed to be able to contribute further to the global environmental goals? So SMR or small modular reactors will be realized. and we will likely see a strong expansion and deployment from 2030. The large-scale reactors of generation 3 and 3+ have for a long time played an important role and will continue to do so in the future. We will possibly see SMRs of the so-called generation 4 develop with an increased demand. Lifetime extension, here called LTO, long-term operation, of existing facilities is ongoing right now and will be important and economically beneficial for a long time. Large generation 4 reactors are also not an impossibility in the future. And talking about the future, we all hope that fusion one day can make a breakthrough. And along with this, power upgrades are also carried out on existing facilities. And another way of visualizing said technologies and possibilities is shown in this picture, linked to the need for further innovation and the level of technical maturity. And from here, I will hand over to Eric to tell you more about where SMR can fit into the industry and how.
Yes, so what Jonas has been telling you now is basically where we are now, and what I'm supposed to tell you is where we are going. So in this puzzle, where do SMRs fit in? Well, the things that make SMRs so attractive is, for example, that you have more options for siting rather than placing it somewhere just to produce the electricity there. You can place it where the need is located instead. The smaller output of power also enables new actors to utilize this. Some actors who may not have, for example, a very large power requirement. This also consequently leads to a smaller capital investment, which enables yet further actors to enter the space. And what is currently being fought for is this simpler licensing and construction effort, which Jonas talked a little bit about with this modularity. And all of this leads to new actors being able to enter the space. And I don't know if you read the news recently, but you have, for example, Amazon and Google moving into X Energy and Kairos Power, respectively. And for me, that's very exciting because my background is advanced nuclear, and both of those reactors are what you would consider advanced nuclear. One is a high temperature gas reactor and the other is a molten salt cooled design. So with SMRs and the ability to locate them on site, so to speak, you have the possibility of utilizing both electricity and energy production. And there are some power plants already that do this today. For example, there are district heating plants in Russia, China, as well as Switzerland, which utilize the nuclear heat from the plant to produce district heating. Another possibility is what's called behind the meter, which is also made possible by placing the production near where the need is, and then you have full authority over the distribution. And in addition to this, many SMRs have what's called full black start capabilities, meaning that there is no need at all to have an external grid connection. And this on-site production of energy enables the transfer of high-grade heat, which cannot be transferred long distances. And here you have a small overview of what's called advanced SMRs, which I mentioned briefly here, and their various output temperatures and their potential applications. So you see you have district heating here being enabled by currently existing light water reactors, but for these more exotic designs, you have a whole host of different chemical processes and other things which is unlocked. So what people like to mention nowadays is what's known as the clean energy economy. And a lot of this is centered around hydrogen, which has seen a slight downturn recently. But for hydrogen production, SMRs can be seen as particularly attractive. And we all know hydrogen as you can make use of it as a clean fuel, an energy storage material, a hydrocarbon building block. And the current way of producing it, this is a byproduct from natural gas extraction. And this is still quite a booming sector where $3 billion were invested in electrolyzers in 2023, which is a 5-time increase from 2022, with an additional 150% increase projected for this year. And To reach this net zero scenario, which Jonas spoke about, we need about $50 billion invested in these electrolyzers. So beyond the electrolysis way of creating hydrogen, this high-grade heat produced by some SMR designs also enables thermochemical hydrogen production. And this is a higher efficiency compared to water electrolysis or even high-temperature electrolysis. However, this method isn't commercially proven yet, but has been shown on lab scale to work. Recently, the IEA published an SMR booklet updated for 2024, which has a section highlighting the versatility of SMRs in production of energy beyond electricity, and also their use for hydrogen production. Another part of the clean energy economy is battery storage and cooperation with renewables, because I think it's important to stress that SMRs are not going to be the complete solution here. This needs to work in conjunction with renewables as well as storage technologies. And nuclear's contribution in this is that it can provide what's known as base load, or it can increase the resilience and thus stability of the grid. As you can see here, we have the hourly electricity production of France, which is known as a very prominent nuclear country, with nuclear here in purple providing the base load, with renewables working during the day to match the load. What's important also to mention when speaking about battery storage is that batteries have lifetimes and there are limits on the raw materials available. And if you compare this to SMRs, SMRs are generally adapted to operate for up to 60 to 80 years and require minimal upkeep beyond refueling. But this also, they need to work in a complementary way to be able to make this puzzle go together. So as Jonas mentioned, we're going to give an example of an SMR case study workflow. This is structured like an amalgamation of several real assignments that we have had, which we have baked into one. So this would start with making a technology choice, because the choice of using an SMR is not a given, because all options must be looked at. For example, making use of the existing grid, which may be more complicated in some places due to remote locations, energy storage through hydrogen or batteries, as well as fossil fuels for a comparison. And the siting, sometimes it's decided by the presence of an activity, for example, a mine or a gas refinery or oil refinery. However, despite this, you must make a closer siting decision to be able to exactly position the facility. And for this, we have tools, internal tools of WSP called, for example, GoldSET, which I will describe later. This follows then with the feasibility assessments. And these are essentially multi-pronged assessments of the general feasibility of the plans with a focus on certain highlighted crucial topics, such as geology, land use, environmental permitting, infrastructure, etc. And this is using both IAEA documents as well as local legislation. This all is baked into the planning and performance of further studies, such as, for example, environmental impact assessments. And these are then used to proceed with the project beyond this point and essentially break ground. So technology choices. There are some parameters which go into this. For example, the target availability. We need to know what the client actually wants and whether SMRs are able to fulfill those requirements. Nuclear can provide very high availabilities, like 90–95%, but it can be found unsuitable if a very high availability is desired, for example, over 99%. There are some solutions for this, such as multi-unit SMRs, such as the one developed by NuScale, or choosing a more available type of power, which then comes at the cost of CO2 releases. The location, does the client have any suggestions in mind? It's good to narrow down a little bit this location evaluation process. However, some of these suggestions sometimes come back as quite poorly suited, which is why we like it when they leave this up to us. And other parameters which may go into this is that if the site is, for example, especially remote, the location will influence the technology choice. As for example, you need to transport fuel and waste away and to the site, which may be very complicated if it's very remote. The purpose of the SMR must be nailed down. This can often be modified due to the modular nature of the facility. NuScale, as I mentioned before, they offer process steam up to over 500 degrees, which is not possible without modifications on an electricity producing reactors. And some other developers are also making their designs more versatile by having a separate nuclear island. It's called, like, for example, TerraPower, which has already broken ground despite having no nuclear license yet. If you need a higher availability than what nuclear can offer, there are enough reasons to still go with nuclear, but you may need some form of supporting power supply, as this needs to replace the full output of the reactor. Unless a grid connection is possible, this is not a very economical choice. The question of storage, whether there are peak and low periods of your demand, is also another thing which comes into the technology choice. So, and with SMRs, there's also the question of operation and economical choices. So beyond the availability argument, there may be other reasons to go for another type of power production to fulfill the client needs. So if the desire is to employ industrial heat, it limits any reasonable alternatives to fossil-based ones, as well as SMRs then. And while some clients approach us with an idea in mind already and they want to look at SMR specifically, we generally also make an assessment of viable alternatives. And while SMRs are cheaper to deploy, the whole cost, so to speak, it's still a big investment. And recently there's been some issues with cost overruns. For example, NuScale with their Utah Associated Municipal Power Systems project, which saw withdrawal of participants and cancellation. But as described before, SMRs try to negate the economies of scale by standardization and modularization of the construction philosophy. And there will be a time period where you have a sort of lessons learned phase where the cost starts coming down. But in the initial phase right now, where you're building first of a kind plants, there's going to be a higher cost for this. But there has to be a first mover for this to work in the end. There has been endorsements from the EU labeling green nuclear as a green energy technology. And there's been also recently the statements by large financial institutions that nuclear energy must triple by 2050. This pledge was co-signed by yet more nations now during COP29, which is currently ongoing. And all of this should work to bring the levelized cost of electricity down. The on-site placement of the SMR facility also makes it a bit more of a question who owns and operates it. And many developers offer an option of owning and operating the plant with no involvement from the user of the power. And this reduces the requirements on the user of the power, who would otherwise have to employ, train, and certify the operation and maintenance personnel of the plant. And in most cases, this will be a complete offshoot from the main business of this operator, which is why this option is so attractive to many. So as I mentioned previously, this is GoldSET. This is a high-level overview of the siting process utilizing GoldSET. So there are 5 main steps, starting with selecting the best technology, as I described previously. This needs to fit the purposes of the project and is key to defining the project requirements for things like space or area use, existing infrastructure, and workforce. For SMRs, there's a much smaller area size requirement than for many large-scale facilities, as well as requirement for the workforce, where some developers quote less than 100 people for operational staff per reactor. And once you have the requirements, you can begin to define criteria and indicators that support the site evaluation steps. And from there, we use a number of siting criteria, including technical requirements, engineering, safety, environmental, cultural, social criteria, to identify the most suitable areas through the application of the GoldSET spatial model. And this is an example output here, where all indicators are combined to create a visual map, where it's visualized as a heat map, showing areas of high and low siting suitability. And this allows quick decisions to be able to determine where the most suitable spaces of land are. And this has been used to site nuclear power in Canada. It's also a very versatile tool for siting industry as well as infrastructure such as roads. From deciding, we move on to the feasibility assessments when you have a final site in mind. And early GoldSET siting recommendations and rankings they're based on somewhat superficial data, where it's classified into 3 categories: positive, negative, and excluding. And once you have a set of candidate sites, you have a deeper look into each of them. And a site can be selected as most suitable, however, the precise parameters of the site must still be elucidated. And as Jonas mentioned, WSP has 70,000 employees, and many of them are not, or most of them, are not directly involved with the nuclear field. Their field makes them invaluable in a study such as this anyway, because of this multi-pronged feasibility assessment. We have performed many assignments where we've had to pull people in from outside of the nuclear field and use them with very good success within these different assessments. And this includes, for example, environmental advisors, land use planning experts, geologists, etc. And these are just a couple of examples where we've found luck with this type of model. So some key takeaways from this presentation is that at this stage, it's not possible to provide, no, hang on. Yeah, so SMRs, they have a very large role to play in the future clean energy economy, both in providing electricity, but also in providing industrial heat to users, which is facilitated via this on-site deployment. The design philosophy of trying to negate this economy of scale has potential to provide cheaper power to many more actors of smaller size. And this push toward green stamping the technology by the EU, as well as the statements by financial institutions and governments around the world, serves to intensify these investments into nuclear, and can also lead to more favorable loan terms for new operators. And this is really the key aspect in reducing capital investment costs for this. And yeah, simplifications in the technology will also work towards this, not only this modularization, which we explained before, but also the simplification of the designs themselves, where you have a lot of designers putting faith into passive circulation, for example, and essentially trying to keep the facilities with as few points of failure as possible, and thus reducing the capital investment cost. And with that, I would like to thank our audience for listening, and I would like to proceed to the questions section of this presentation.
Thank you, Eric. Thank you, Jonas. You had a stimulating presentation. We have lots of questions, so let's just jump right into them now. Okay, first question. Have SMRs been used or are being considered to be used to power electrify railways? If yes, would there be any benefits to, say, a local community with the heat rejection, combined heating and power, CHP, from the SMR? So who wants to take that on? Oh, I can speak from the Canadian standpoint, globally. SMRs are sort of very brand new, so they haven't been applied yet, but they are being considered where we have railway lines and commuter lines that have already been or being electrified. So yes, it's being considered, and I think you have a really good point here on what you could do for a host community. Because as if you have longer lines, you're going to need more power to generate to move those vehicles. So having them along the lines will be a great idea to be able to do that. And with the offtake of combined of heat, there could be an added benefit to the community. So I think that's a great idea. And I'll probably use that in some business development ventures that I'll be going forward with. Eric, Jonas, any thoughts?
No, I think that sounds very nice. There's been a lot of recent developments with district heating type reactors, which would be something which would be quite suitable for this this suggestion here in this question then.
Great. Okay, let me go to the next question. What about the waste from SMRs? What are your thoughts on that? What kind of waste do we get from SMRs, and what do we do with it?
So light water SMRs produce the same type of waste as a regular full-scale light water reactor, and the amount of waste per produced unit of power is higher due to it being a smaller core, and it uses the fuel a little bit less efficiently, and it also leads to a bit more activation products per unit of power. But today, the waste itself is not seen as that big of a concern. There's been multiple countries breaking ground on fully capable solutions, such as Sweden with the Forsmark final repository and Finland with Onkalo. You also have a lot of people, when they talk about nuclear waste, they quote this figure of, okay, you need to guarantee the safety of the waste for 100,000 years. Well, after only about 5 centuries or a little bit more, the hazardousness of the waste has decreased to the point where you essentially need to get it in your body to experience significant harm. There's also, I can just take some examples from what we're doing here at WSP. We've done evaluations for waste production of SMRs using Monte Carlo simulations, and we've also been an integral part in developing this KBS3 waste treatment model, which is currently being employed by Sweden and Finland for their final repositories. And another thing which I also like to bring up when people ask questions about nuclear waste or state that nuclear waste is such a problem, after these 100,000 years, the waste has reduced its hazardousness down to what natural uranium ore is. However, mining waste from other companies, such as, for example, lead, mercury, arsenic, is still going to be lead, mercury, and arsenic after 100,000 years. So that's something a lot of people forget, and I think there's been too much focus on nuclear waste as being especially hazardous. And I think it's a bit unfair considering the vast investments and engineering efforts which have been employed recently to reduce this potential harm.
Great. Thank you. Another question, and this is a technical question for you guys. Do SMRs have a passive cooling system? That is, no additional power source is needed to cool it down in case of an accident?
That is dependent on which design you are talking about. Some of them are what's known as completely walk-away safe, and that means that you can essentially, well, you can just walk away, and the reactor will not only turn off itself, it will reject waste heat to the point where no intervention is required, and it will just simply turn off and cool down. Some of them, or I should say most of them, have walk-away safe periods. Like, for example, they say that it will be fine for 3 days, it will be fine for 1 week. Some of them are limited in that way, and I think those represent the majority. I think also, yeah, most reactors today, I would say, have this capability of being walk-away safe for at least some period of time. You have redundancy also with external grid connections, as well as diesel generators on site to be able to provide any required power which is needed to cool down the reactor in the event of an accident.
Great. Somewhat simpler question. How small can SMRs go down to? We know that currently Westinghouse is developing the eVinci reactor, which gets you down to about 5 megawatts in size, which is about the size of a transport truck. So do you think they can go smaller than 5 megawatts, guys?
Well, I mean,
Yeah,
you're entering the realm. Yeah.
When it comes to like a nuclear reactor, you can make it pretty small, and you already do that. You can look at, like, in the submarines where you have been using nuclear reactors for a long time, and also the development to have it on that kind of on ships and so on to provide electricity. So I think you can make it small, and it's also the thing that it's small that makes it easier to make it that the modularization, it will be easier as well. There's more like the bigger you get, the harder it will be to do the modular part of it.
Mm-hmm. Okay.
Yeah, and in the realm below SMRs, you have what's known as MMRs, which are micro modular reactors. And really, there is no lower limit for what you can do with a nuclear reactor. I personally brought a reactor to 200 watts of power and held it there as part of a training exercise. But I don't know how useful it is.
There's always going to be an application for something. Thank you. We've seen a lot of questions regarding to security with SMR. So security risks such as terrorist attacks. What are your guys' thoughts on those? It's a big hot topic.
Well, like other nuclear facilities, you have the same defense in depth principle for SMRs, where on the nuclear safety side, you have the sort of boundaries to prevent the release of radionuclides. You have the fuel matrix, you have the fuel cladding, you have the primary coolant system boundary, and you have the containment building itself. And that's the same for SMRs. Those are all still there. Now, if we're talking on the nuclear security side, you're talking about the 5 Ds, which is detect, deter, deny, delay, and defeat. And for SMRs cited in the normal way, if you could say that, you have pretty much the same situation as for a regular large-scale nuclear power plant. However, for a more remote siting, when there's a longer time to expect any help, for example, you need to put more emphasis on this delay part of these 5 Ds. Now, I should say also that modern nuclear reactors, they're designed in a way where even a highly competent adversary cannot control it in such a way that they would cause the release of significant amounts of radioactivity just by operating the plant in the wrong way. So the attack vector is going to be external damage, and nuclear reactors are protected with inches and inches of steel and concrete and earth, preventing the penetration of this primary containment as well as the reactor vessel. Personally, I feel like the risks are a bit exaggerated, especially with the additional requirements after 9/11, which require all containment buildings to be able to withstand the impact of a fully fueled jet airliner without release. And this requirement also applies to SMRs, and is one of the reasons why we've seen these design modifications recently with SMRs, which started out quite small, got sort of brought back to reality and realized they needed to add more concrete and steel to be able to conform to these requirements. And some of them have a bit more clever solutions. For example, GE Hitachi, who have the reactor building essentially located buried deep below ground to be able to conform to this aircraft resistance criteria without adding too much material.
Great. Do SMRs use a similar uranium fuel as the large nuclear plants, or a different uranium enrichment process is needed? Guys?
Jonas, do you want to?
Yeah, I was on mute, sorry. Yeah, so the light water reactors will use the same type of fuel, and it depends a little bit on what if you look at advanced reactors, it will differ. And there are some of the advanced reactors that need an enrichment that is quite hard to achieve, or at least there are not that many factories that are available doing that kind of fuel. So we also see some of the reactor developers going from one type of fuel to look at another type of fuel just to get it commercialized easier and faster.
Yeah, I can add that the enrichment process is performed on what's called uranium hexafluoride, which is essentially the uranium in a gaseous compound. And no matter what it's going to end up as, whether you're going to use metallic uranium fuel or an alloy of it, which I think TerraPower are going to use, whether you're going to use it in regular uranium dioxide pellets as used in most reactors, or whether you're going to make TRISO fuel, this tri-structural isotopic protected beads of fuel. The enrichment process will be the same. It will just be more work intensive to get it up to these higher enrichments. So today's reactors use about 4% enriched uranium, but some advanced designs like the advanced SMRs go close to, but not above 20%, I should say.
Good. Okay, last question. Can we expect well, not, that was the wrong question, pardon me. Sorry, having a little computer challenge here. Have there been any improvements in, no, not that one, sorry. There's a lot of questions in here. What are the key challenges with this in terms of route to market where there hasn't yet been an uptake of this opportunity? If you need me to repeat it, let me know. Eric, Jonas?
Yeah, I have so many windows here. So one thing that many SMR developers don't seem to consider, they're so stuck in their design process that they haven't really considered who is going to build the thing once it gets to that point. And the move to SMRs is where the modular becomes important in the fabrication of the units here. And there's a global lack of resources within the nuclear field, which will be a challenge in the future. For example, if you're looking at the dimensions of the reactor pressure vessels, which remain large for some SMRs, there's only a few forges in the world which are able to make these currently. However, there are some advances recently. And the other challenge is cost. It's a highly capital intensive project with very long-term outlooks. So yeah, I see we're nearing the end of our time here.
Yep, we are at the end of our time. So I want to thank you for your participation, gentlemen, and very much thank you to our audience for attending this. We appreciate your time, and you'll be able to find this presentation and additional information in the box. So in the handout boxes. Anyways, so thank you very much for attending. We look forward to hearing from you. All the questions that have been sent to us, we will address each and every one of them. Thank you again. Take care.